So something in the exercises, right? You had this scenario where you had the probe qubit was running for some time t or delta t, I don't remember. Then it was measured, right? So we get some output here, x, and then at this moment you would prepare a new probe, yes, and do another measurement, so x1, x2, and this continues to. You can do it n times, right? So you split your total time in these things, in the small intervals, and basically you just have independent runs. So in the first run you prepare the initial state and you do it all the time, and we just even say we have the measurement is the same. And then you use the bound, right? So at the end here we have, at the end, right, we have the field is either on or off, so b equals 0 or b equals some constant. And this is just always is the case. So here at this moment, because the final state is just either rho or no, rho 0 or rho b, right? And this is, then we have n copies of the state. So the bound you used, I guess, is to look on the trace distance between n copies of the state, right, for the zero field, and n copies of the other state. Yes, this is the bound you used, I guess. And we know that it's upper bounded from the fidelity like this, 2n for a single copy, 2n fidelity of a single copy, and it's lower bounded by 1 minus the fidelity of a single copy without the square and without the square root. So rho and rho b, like this. Yes? Now you might wonder, right? Because this is a bound on the trace distance between these two states, simply. So between the copies of the states. So it doesn't tell you that actually these bounds are valid if you're forced to do just sequential measurements. So you have to measure them independently. In principle, it could be that this is like a global state, this is a global state. It could be that this is only attainable with a global measurement in one of the directions. Yes. So now I just like to start by explaining that actually you can also, this bound is also valid for just sequential measurements. Okay. So that it's, I think the exercise then becomes clear, because what we really care about in this scenario is to do the sequential measurements and then to quantify the bounds of probability of guessing. Whereas this bound, if you look at it like this, it doesn't really have a restriction on sequential measurements. So let's just start with this, and then you also, since you have the exercises after, this will be also a good warm-up, I guess. Yes, and it's actually very straightforward, I think. At least one direction is really straightforward, because, so again, what we really care about is to bound the trace distance for sequential. So the trace distance is sequential measurements between these two states. Okay, rho 0 and rho 1 n copies. Well, first thing you can notice is because this is a distance between things which we attain with some class of measurements. Of course, the distance is lower bound on the trace distance between states, right? Rho 0 tensor n and rho 1 tensor n. So about this bound, I don't have to worry. It's directly bound, right? So we can just use this 1 minus f to the n. Okay, so this is the kind of this direction. Now for the other direction, it's a little bit more tricky, because in principle we say, aha, this is a lower bound on this quantity, but maybe to attain this lower bound, to attain this distance, we need some entanglement measurements, right? But let me just show that it's not the case. But this is, so to do so, we just actually consider this quantity. So let's just look on this quantity, right? 1 minus f of rho 0 and rho 1, okay? And this we know that this is attainable to the power n. This is attainable by some measurement. Some measurement on a copy, on a single copy, yeah, because it's just to the power n, because we have the copies. So this actually is equal to 1 minus f between some, so we fix the measurement here, m. This is the measurement which maximizes this quantity, right? So which attain this quantity. So then we just get the probability of 0, so to say, the probability of output which corresponds to the density matrix 0, where there is no field, and the probability 1, which corresponds to this state with the same measurement m bar, all right, to the power n again. But this, of course, is like just quantifying the trace distance. We've seen it for a classical, so for probabilities, right? This is just like having the fidelity between this direct products of these probabilities, right? So p0 to the power n and p1 to the power n. Okay, sorry, this is the fidelity. Okay, so now Now, this is again for this particular measurement, but of course now we can just use the fact that this is a lower bound on the trace distance between the same probabilities. So this is a lower bound on the distance between this guys, okay? P1 to the power n. So in other words, we showed that this quantity we had, we computed in the exercises, it's a lower bound on the trace distance attainable with this measurement, sequential measurement m. Right? It's actually not even a sequential measurement, it's just a product. So yeah, it's a sequential measurement. Product measurement. There is no feed forward or something. But of course, kind of the trace distance I can get with some measurement, it's a lower bound on the trace distance I can get with any sequential measurement, right? So simply this is just a distance between, a bound on the trace distance between the states. So this quantity we're interested about 0, 0, n and rho 1 to the power n. Because that's the best trace distance I can get among all sequential measurements, and this is just one realization. Picking the measurement which attains this, right? So that's it. Now we have the one direction, the other direction, so we can just add here that this is indeed bigger or equal than 1 minus f to the power n, right? So just to, in other words, what you did in the exercise is actually really corresponds to the bound we care about. What's the best way to distinguish these two situations? By repeating n times the experiment. Yes, because it's really like this. So we're kind of interested about this quantity. Because in general, it's lower, of course, than this one. Right? Is it fine? Or I don't know if you were wondering about this or not. But now you shouldn't. Good?
Good.
Good? Good. Okay. Yes, so now we can start our next topic. And actually, there will be no more quantum states for today. Because again, it's like in the beginning, we are going to back to a classical parameter estimation. And this is the title of the lecture today. What is it? Lecture 5, I think. This is parameter estimation. So we'll start with just a classical setting. And next week, we will lift it to the quantum case. But there are many things to know already in the classical thing, in the classical situation, right? Which I think you don't know about. So it will be quite interesting. So now, what we did consider until now? What was our kind of experimental scenario? It was that we had basically always two possibilities, right? Typically, we had like either the field is equal to 0 or a field equal to a constant, right? And then we prepare a probe there, and the probe kind of interacts with the parameter, so right, with the environment which encodes the parameter. And then at the end, well, we had a quantum state, but classically at the end you just have a random variable, so imagine you had a random variable which depends on the parameter, right? So in other words, the random variable is just the outcome. So the random variable is characterized by the probability of outcomes, right? This is just the probability which depends on the field. Yes, so the distribution of measurement outcome depends on the value of the parameter. And so far, we only considered the case where really there are just two possibilities. There are two probability distributions. The one for b equals 0 and the one for b equals something else. And we wasn't quantifying things like, okay, what's the best way to distinguish them in one run, and then how does it go when you have many runs? Yes, so this is sometimes called hypothesis testing scenario, because you really just have two possible situations, or one or the other. But of course, you can imagine that it's in many cases, like actually the field doesn't have to be in just two possible values, 0 or b. In general, it's rather something, a continuous value, right? Which is in some range. For example, you can know, okay, b should be in some range, and I don't want to guess between two cases, but I actually want to measure it. Okay. So this is exactly what we're going to start doing now. So now we have so the value of the parameter. The value of the parameter is in general continuous. However, we will kind of assume that we have some prior information about this, okay? So we will assume that we have So this is like a prior probability. Prior probability. So to start doing something quantitative, we have to assume that we, in the beginning, have some guess about what this parameter can be. For example, we can say, okay, you know, it's like a field, so maybe its value is between 10 Tesla and minus 10 Tesla in our experiment, right? Because simply it just cannot be larger in this particular context. Same as for the temperature, you say, okay, maybe my temperature is not bigger than 300 degrees, right, in my experiment. So when I measure it, or this is one possibility. So this will be like a flat prior. Yes. So actually, a prior probability is just like a probability. We will call it P0 of B. This quantifies our original belief about the value of the parameter. So this is kind of the original belief about the parameter, the value of the parameter. So basically, you can say that so far we had a particular situation where the prior was just two delta functions. So we knew that the parameter was with 1/2 probability equal to 0 or with 1/2 probability equal to B. But now we'll start dealing with cases where actually it can be like some continuous probability distribution in space. Basically, the best kind of, if you want to really isolate, the cleanest way to think about this prior is like, let me just draw a diagram then. So for example, let's say there is really someone. So the cleanest way to think of this prior is that, okay, so I have still my scenario where I'll measure my field B here, right? But there is someone else here, some referee. He actually prepares this B, and the recipe he prepares it is completely known. So you know that this person here, it really just draws the value of chooses the value of the field B from some probability distribution P of B, right? So this is kind of your premise, right? This is, you're sure that this B will occur with these probabilities, and still your goal is to know which P was prepared in this experiment, right? Is it clear for the prior? You've probably seen it in some statistics or something like this, right? So now we have a prior probability. Prior probability P0 of B. Okay, now we know something else. We actually know the physics of our thing as before. So we know that, well, I will draw it again once again. So we actually have a model for our system, right? Like for example, you use this qubit model with the master equation. So we know exactly, this is one thing. The other thing is conditional. So conditional probabilities. Conditional probabilities. So in other words, what we know is, given a value of the parameter, right? We know the distribution of the outcomes. Because we know the physics. The only thing we ignore here, so basically we're dealing with a parametric model. The only thing we ignore here is really the value of the parameter P. Otherwise, we know exactly the physics. So for a given B, conditional on a B, we know exactly what these outcomes will give. And yes, so this is really the two things we know. We know the physics of the system, so we can predict the outcomes, the probability distribution of the outcomes of our measurement variable for a fixed field. And we also know how the field is prepared, right? Or we have a guess about what its value should be. Now the question is, of course, what we care about is actually what we want. What we want is the other way around. So what we want is to know the probability of B given our observation. All right. So what we want is actually to see, once we observe something, is to relate it back to the probability of B. And this is kind of the Bayesian analysis now we're doing. You have questions on? We want to estimate the parameter. So what we know is what we observe is the outcome of the measurement, And one way to quantify it is really just to update the knowledge about this parameter. So in this sense, we can use the bias rule, right? Do you know the bias rule? So let me tell you about the bias rule. And this is very simple. So we just say, well, if what we care about is the value of the parameter conditional to the outcome, yes, to the outcome of our observable x. Well, this by definition, this conditional probability is basically the probability of the joint probability divided by the probability to observe the outcome. Okay. This is precisely the bias rule. Now, this thing I can again write it as in quantities which I know. This is a joint probability to have the field value b and observe the outcome x. So basically, it's just simply the probability to observe x conditional on b times our prior distribution of b. Right? Finally, down here, what I have down here is the overall probability to get the measurement outcome x. So again, I can just express it because I know that the overall probability to observe the outcome x is just given by the integral of the probability for having this outcome x for a given field times the distribution of the field, right? So this is again a quantity I know. So in other words, in principle, if I know everything, so let me remind you again that in principle, we know that we have the prior distribution and we also know the physics. So we have a parametric model. And from this, we can just use this bias rule. And after we do our measurements, we update the knowledge, the distribution of B with what we know, right? This is called the bias rule. And this gives rise to the Bayesian statistics, right? And all the Bayesian analysis. And we'll come back to this later a bit. Is this clear?
It's clear.
Did you know this formula already? I guess so, no?
Yeah.
Yes, okay. Now, you see the problem of these things, sometimes that actually it's not so easy to compute, especially in scenarios where you have many, many repetitions, which typically is what we're interested about. Because you will just, every time you will have to do this update rule, right? This is one thing. Another thing, then you will kind of, from the beginning, think about the optimal scenario, about the optimal strategy, which at the end will give you the best estimate of your parameter. Moreover, actually, in the asymptotic case, you always can get a simpler treatment. You don't need to do this like this brute force with the bias rule. And this is actually given by this estimator language, which I'm going to introduce. Okay, so now we are moving forward a bit, and we will kind of look at this a bit differently on the same problem. First, let me maybe just summarize what we have. All right, so just to draw, now what we have is that we have our probabilities. So we have our simplex of probabilities. Now what we're describing is a curve in this. So this is, for example, let's say the probability of the first outcome, right? This is like a 3 outcome measurements. A probability of the first outcome, probability of the third outcome, second outcome, probability of the third outcome, and this curve precisely describes our parametric model. So that's precisely the probability distribution of the outcomes, which depends on B. So it's basically kind of, you can just draw it as a vector. This is a curve, it's like a vector on the simplex, which depends on B. Yes? And we actually get we observe this outcome, and we want to guess where we are in this curve to recover B. Okay? This is a geometrical picture of what we're doing. Now, as I told you, let's introduce what is an estimator. This will be what, 3, I guess, or 2, maybe 2 estimator. Okay. So an estimator actually, an estimator definition. So an estimator B of X is another random variable. It's another random variable which kind of is supposed to predict the value of the parameter, which gives an estimate estimate of the true value B from the data. Okay. So just going back to this picture, what we have is like there is a true value of the parameter B. Right now, this true value, this is just a number, it's a parameter, right? This true value gives us our outcome, which is a random variable. This is a random variable which depends on B, and it's precisely characterized by this probability distribution, which we know. Okay. So this is what we observe. This gives you the data, and from this you want to reconstruct B. So we can define a function, right? B hat, which depends on this X hat, for example. But actually, just having too much hats, it's annoying. Right? Now, what we want, of course, from this function is that this function gives us the true value, right? Because we want to estimate the true value. But of course, since we're dealing with random variables, you see that this is just impossible to do it always. Because like just if you had, suppose that, yeah, because just this, the same B can give you different outcomes. So if it's a non-trivial problem, then you will always get for different B's, you might have the same outcomes, and you will not know how to reconstruct it, right? So we cannot expect this B to give the true outcome always, the true value of the parameter always for each outcome, since this is just random variables. But actually we can expect it to give the true value on average, right? And this is called an unbiased estimator. And actually we'll really care about unbiased estimators. So you can really think of it as a game. I do my measurement, I get an outcome, and then from the outcome I observe, I make a guess on the value of the parameter, right? But of course, this mapping here, you can define it. You will define it before you even do the measurement because you know all the probabilities. So that's what we're doing here. So now let's go with unbiased estimator. Unbiased estimator. This is so estimator is an estimator B, right? Is such that the expectation value of B of X minus the true value is equal to 0. Okay. What does it mean? It means that okay, well, eventually, if I just throw my coin here, for example, and I try to estimate the probability of tails, I might be wrong. But on average, right, if I take the average or all possible outcomes of the measurement, I will actually get the true value. So it means that this is actually what the kind of estimators we want, these unbiased estimators. All right. Finally, another definition is how to quantify the precision of the scene. So even having two different unbiased estimators, they might be different. It's kind of so. What do you think? What's the way to say if this is precise or not? What do you usually do? So now we have the average value of the estimator is equal to the true value, so it estimates the value. Now, how would you quantify the precision of the scene? Any ideas or any suggestions? So let's, right? No suggestions. Let me just draw it then, just so we go slowly. So let's say this is B, so this is the value of the parameter P, and let's say in my experiment, really this is the scene. So now around this B, the estimator now, my estimator kind of, let's draw here the probability to get an estimator B hat, okay? And so what we said is that, okay, so basically you can have them kind of somewhere around here. On average, it is the true value, and in general, you get kind of the probability distribution around this. So the estimator is also quantified by just the probability distribution to get a particular value. So we know that this probability distribution average is actually the true value. Now, how do you quantify kind of the error you make in such an estimation, or the expected error? Like this is the very usual thing. Let's say it's a Gaussian here around. How do you quantify the error that the Gaussian kind of makes about its mean value? No suggestions. Well, you can just take the variance, right? Basically, the next thing you know that the average, the mean value is the true value, which is good, so the estimator is unbiased. Now the next point you care about is, okay, on average, how far will I be? How far will I be from the true value, right? If I do my experiment on average, all right? So this defines the error or the mean squared error. So this defines that the estimator is a good estimator because it converges to the, in general, on average, it gives you the good values, and this thing is a mean squared error. Mean squared error of an estimator is just, well, the mean squared error. So we just take the value for a particular outcome x minus b, we square it, and we look on the expected value. Okay, this is called, we'll call it the mean squared error of our estimator. So this really quantifies basically how far on average I will fall. What will be the average square distance from the true value if I do my estimation experiment. All right, so it's very, I think it's very natural to quantify this, to things like this. Is it clear? So now we define it. Do you have guys questions on this point, or we continue? Are you around?
Yeah.
I don't hear you. Yes.
I think it's clear.
It's clear. Okay.
Yeah.
Let's just continue. So now I think the best thing to do now is to make a simple example. So these things become kind of a bit more clear, or at least we can just play with them. So the simplest example I could think of is a coin toss. Yes. So just keep this in mind. We have this unbiased thing. Average is convergent, and just the deviation from the average is a mean squared error. We'll also call it just precision because it's shorter. So let's start with a very simple example, and then see how things appear there. And then we can kind of generalize our conclusions from this example and define some more useful stuff. Good. So the simplest example I can think of is a coin toss. So let's say we have a coin here. So our experiment is just we have a coin, right? And we toss it. So and then we get either a tail or a head. So basically, our measurement has just two possible values. So it's a two-valued random variable, and the probability. So for this coin, right, the probability of having a head. This is just some function q of some parameter b. Okay, and the probability to having a tail. This is just the other one. So 1 minus q of b. This is our rule. So this is the simplest instance of what we were just discussing. We really just have two possible values that we can observe, and the expected value, so the probability of this outcomes depend on the parameter. I mean, again, for a coin, it's not so difficult. It's easy to imagine that, like the coin, the probabilities depend on some value, but just for some binary process, basically that's always what you get. No, I don't know. Like the probability to get infected from someone else. No, this typically depends on the R factor of the disease or something like this, right? Okay. Yes, and now we'll do. So we'll try to see to construct an estimator for this and see what's the error. However, we'll actually assume that we do. The thing is that we do n repetition of this. Huh? So we have this coin cost. So what we do is we do like do n. So we do n times a coin. We do n coin tosses, and try to estimate b. Okay. Nice. So we will actually decompose it into steps. First, we will just estimate q. We'll see how we will estimate q, which is really straightforward. And then from this, we can see how from kind of an estimator of q, we can construct an estimator of b. So first we'll estimate q. So first, well, I guess you all agree that the probability, so after entering causes, the probability to have observed small n heads, or let's say small k heads, probability to get k times heads is given by the binomial distribution. So this thing is, right? This is K, kind of, if you have n, overall n flips, right? You agree that this is just K times Q times 1 minus Q, the other one. So this is a probability of one particular instance where the heads and tails are in a precise order. But of course, there are many instances like this. And the number is given by the binomial, right? So times n choice Q, choice K. As you see, since we just repeat the same exact experiment now, really the order in which heads and tails appear don't matter. The only thing that matters here, the only thing which can relate to B, is really the total number of Ks, of heads, and the total number of heads and the total number of tails. Very good. So now this is kind of our parametric model, right? Because here precisely this is the probability of our outcome, and it depends on B. We are this function Q. So how do you estimate this thing? Let's construct an estimator. Let's first basically, so let me just first draw it. No? So this binomial distribution, as you probably know, for large n, it's really given by Gaussian. So just to draw it, it's easier. So P K of n. For large n, this is really approximately given by a Gaussian distribution, so 2 pi. And then I think it's like something like pi, Q. Q, 1 minus Q, probably times n, times exponential of minus K, minus the average. The average number of heads is, of course, just Q times n, divided by 2 times the variance. There is a square root here. Wait, let me check this quickly. Q1 minus Q times n. And the square here, right? Well, we actually don't need it. This is just to help you kind of represent this probability. I don't know if you're familiar with binomials, it's also very fine with binomial distributions. Okay, yeah, so just the only thing which misses here is that the square root goes all the way here, right? So if you now look on the distribution, so this is probability of K of heads, so this is binomial distribution, and you see it's centered at Qn. This is probability of K, and this is K, right? It's centered at Q times n, and the variance here, the variance of the distribution is Q times 1 minus Q n. Okay. So, well, basically we see that since, can you now guess an estimator for Q from this plot, right? Any suggestions? How do you estimate Q? So we get this K heads, right? K is the thing we observe. So now we need an estimator. An estimator, first of all, I said we will construct an estimator for Q. So we have an estimator Q, which is a function of K. How do you construct one? Looking at this curve. Any ideas? No? Well, you see, but so this is like the number of heads is so roughly a Gaussian distributed around the mean value Qn. So a very good guess is just take this number and divide it by, so let's just take K and divide it by n, okay? Because then the expected value of this thing is precisely given by Q, right? The Q is the average. So it's basically the frequency of heads, right? As you can expect, the frequency of, you do a coin flip many times, the frequency of getting a head is precisely a good estimator of the probability to get a head. Like, this is just basically telling you that the frequencies will converge to the values of probability in the long run. Yeah, so this is a good estimator for our thing. Now let's see what's the error of this estimator. The mean squared error of this estimator. So first, you agree that it's unbiased. Okay, let me draw it again. So we had our Now let's look at the frequency k over n. It's also a Gaussian thing. K over n is as a frequency, right? Frequency of heads, and we define our estimator q hat of k simply equal k over n, the frequency. Right? It's actually again it's just another Gaussian it's also Gaussian normally distributed variable. And to compute the mean squared error, we just look on this average. Mean squared error of this estimator, right? This is just simply given by, we take the definition q hat of q minus q square. Okay. So in other words, let's just use the Gaussian approximation. It's simpler. We get, okay, let's just first write this as a binomial. So this thing is sum of p of k, so the probability to get k n times k over n minus q squared. All right. So you see that this is just given by sum of 1 over n squared. I put the n out of the brackets. Sum of p of q n times k minus qn square. Okay, and this is just the average of the binomial distribution. So here we get the variance of the binomial distribution, and again this is just given by the variance of our Gaussian. So it's 1 over n squared times the variance of the Gaussian, which, if I remember correctly, was p. No, sorry, not p, because q, right? Q. 1 minus q to the power n. Not to the power n, sorry, times n. So just to remind that the binomial distribution is roughly given by Gaussian, which I wrote previously. Now we have raised times n times exponential of minus k minus qn squared divided by 2p 1 minus p. So here you get the variance, right? So this is precisely the variance. Well, so in summary, this is just the mean squared error of this estimator is just given by the variance. So if you divide by n, it will be q times 1 minus q times divided by n, right? Because we had this 1 over n thing, right? So you see, this is the very usual thing you see here, that in n at least, that the variance goes as 1 over n, but of course then the mean deviation goes as 1 over square root of n, like I used to for equity measurements, right? This is how things converge. All right, so now we have everything for our estimator of q. We see that it's unbiased and we get the error. But however, what we originally want is to estimate the field, the parameter b. Right? So the next thing we have to do is to define an estimator. So a good estimator for b. A good estimator for the probability b. Okay. Well, and again, one candidate we can use, which is very natural, because now we have our function, right? Remember, we had the field b, and the coin, the probability of heads was really a function of b. So one thing we will assume now is that actually this function is invertible, because we want that an unbiased estimator exists. So we want that in the range where we in the range which we care about, this function q of b is invertible in such a way that we can kind of backtrack. Since the only thing we can which appears in experimental data is q, we want to be able to inverse this q so that there is no two. We don't want to avoid a situation where two values of the parameter correspond to exactly the same coin. Otherwise, we just cannot estimate it. So we assume that q minus 1 of b exists, right? So the function is invertible. And then, since this is the case, well, and we have an estimator for q, so a good choice then, a good estimator for b. For b is just basically applying the inverse function on our estimator of Q of K. Right, clearly, because what we have, we can estimate Q, and then just to go back to B, we just invert this function, this dependence. Yes, now, do we have time? Yes, we just have time to maybe see if that is. So, this is, do you follow now, or could you follow this?
Yes, it makes sense.
Yes?
Yeah.
So,
Yeah, it makes sense.
Yes.
flipping coins, we just see that the frequency is basically an estimator of precisely the probability of heads, and then we just invert this probability to estimate the parameter, right? To invert this dependence. So let's see if, so first question, is B unbiased? Unbiased, okay. So to see this, well, we need to, well, just do it. So let's compute the bias of B. So bias of B is really just expected value of B minus the true value. So again, just what I maybe didn't mention is that the bias is a function of the true value, because the bias for different B's could be different. Okay? So it's really a local property. It depends on the true value. So what is the expected value of B? Well, we'll just write it down. So really what we get is K. So this is sum of P of K n, the binomial distribution, times Q times B of Q of K. So in other words, it's sum times Q minus 1 of K over n. Yes, this is what we want to estimate. Now, actually, you see that depending on how this function looks like, this might not be unbiased. Because, for example, if it's very steep somehow, and so because so like now we have a distribution here around these things, and we have to invert it to B. So it might not be unbiased in general. However, if n goes to infinity, let's see what happens. So if n, the number of repetitions really is large, then of course you see this binomial distribution basically becomes delta peak around the mean value, right? It's like a Gaussian, which just kind of becomes very, very. So actually, not this, but the distribution of the frequency converges as 1 over square root of n, as we've seen, to the true value. So basically, in the limit, this becomes unbiased. This goes to 0, right? So kind of for finite n, there might be some bias in this estimator, but at least it's clear that when n becomes large, it's a good estimator. Yes. This is the message. Finally, the last thing, which is the most interesting, is to compute the mean squared error. Yes. So, and this is, I guess, now we take a break, and then we'll do it next hour. No, next hour, it's like next 5 minutes. Okay. So, big question now, which will actually all this example is constructed. So, what is now the mean squared error of our estimator B?